So the next talk is by Victoria Volkova, and she will talk about superluminality in DHOST theories with extra matter.
Yeah, thank you. Good day, everyone. I hope you can see my screen.
Yeah, yes, we can.
Right, great. First of all, I would like to thank the organizers for the opportunity to give the talk today. And I would like to discuss the superluminality problem in DHOST theories with extra matter. My talk will cover the results which were obtained in collaboration with Sergei Mironov and Valery Rybakov. I'll try to be brief with the introduction, but still I need to make one. So what are DHOST theories? These stand for the degenerate higher order scalar tensor theories. And what is special about them is that these are not only the theories of modified gravity, but also these are theories which involve second derivatives of the scalar field. Pi here is the scalar field and x is the standard kinetic term. So as we can see, here I have depicted only the quadratic subclass of these DHOST theories, which means that they involve up to 2 second derivatives in the Lagrangian. Here are 5 elementary Lagrangians, which show all possible combinations of two derivatives of the scalar field. And what is special about these theories is that despite expecting an astrographsky ghost because of the second derivatives at the Lagrangian level, these theories are protected by the degeneracy feature, which implies that there are some special relations imposed on these functions which stand before these elementary Lagrangians with second derivatives. And basically, this degeneracy feature is the degeneracy of the kinetic matrix, which ensures that there is only one scalar degree of freedom. So in total, we still have the normal 3 degrees of freedom in these theories. So far, the most phenomenologically viable one is the 1A, the so-called 1A subclass of these theories, which also involves quite well-known Horndeski theories and beyond Horndeski theories, which correspond here for some special choice for the functions before the elementary Lagrangians. In what follows, I will mainly focus on these theories in the cosmological context. For us, what is special about them, apart from being one of the most general scalar tensor theories with modified gravity, is that DHOST theories enable one to violate the null energy condition, which is impossible with the standard matter. And why is it interesting? The reason is that we need to violate the null energy condition to study such exotic cosmological scenarios like the bouncing universe or the universe starting off with Genesis. Here I have shown the characteristic behavior of the Hubble parameter for both these scenarios. And in what follows, I will mainly talk about this type of non-singular cosmologies. Another tricky thing about bouncing solutions and Genesis solutions is that it requires special attention to make them stable throughout the evolution. The stability at the linearized level is governed by the form of quadratic action, which is shown here. And here, H stands for the standard tensor modes, and zeta is the curvature mode, which is the only scalar dynamical degree of freedom here. And in what follows, I will stick to the homogeneous and isotropic setup in especially flat Friedmann geometry. The stability conditions which rule out ghosts and gradient instabilities immediately follow from the form of quadratic action. And this is just the inequalities imposed on the corresponding coefficients. GT and FT are responsible for the tensor sector, and natural GS and FS are responsible for the stability of the scalar one. All these coefficients are some combinations of the Lagrangian functions, which were introduced earlier, and I will not show them here explicitly because they are quite bulky and not really relevant for the arguments I'm going to present. Apart from the stability, we would like to take care of the propagation speed of both modes, and we would like them to be safely luminal at most. Why so? The answer is quite simple. We would like to be on the safe side and expect a standard UV completion of our theory, which is only possible if we stay safely subluminal or luminal at most. And being equipped with this stability and subluminality conditions, we may try to construct some concrete models of, say, bouncing solutions. And there are quite a lot of such solutions constructed. However, another tricky moment was that Hrandesky theories are special from the point of view, because there is a no-go theorem which forbids their complete stability, modulo a loophole with trying to avoid the strong coupling, which is induced by sending one or several coefficients to zero. Well, this path was explored by, was explored recently within our group, but I will try to also stay on the safe side and go beyond Hrandesky, where the no-go theorem doesn't hold. And in beyond Hrandesky theory and other subclasses of DHOST 1a theory, there were quite a lot of examples of non-singular cosmologies constructed. Let me give a brief scheme of constructing such solution, which we were using in our works. We have used a bottom-up approach. Namely, we have chosen the Hubble parameter. Here it corresponds to the balancing solution, for instance, and we always took the scalar field to be the clock in our system, which makes the kinetic term to equal to 1. And let me note here that in what follows, I have everything in Planck units. The next step is to take the ansatz for the Lagrangian functions in terms of powers of x. I recall that x is the standard kinetic term. This step is important because it restricts our analysis in a way, because by taking this ansatz, we can analyze. We know our model only in the small vicinity of this solution. This comment will be important in a couple of minutes. So what we have now? We have the solution we want to find, and we have the ansatz. Now we need to find the functions which are involved in this ansatz by using the background equations of motion and stability conditions, which restrict our functions. The optional, an additional option is to take care about the asymptotics of the theory. This might be important if one would like to incorporate the model in question into a greater scheme with the inflation or later hot epoch. So one will need to take care of the asymptotics, but still it is optional. And by making use of such a scheme, we have constructed several solutions. I would like to show one of them here. Namely, this is the bouncing solution in beyond Hrandesky theory, which has quite a specific feature of having both coefficients which are responsible for the tensor sector equal to 1, which makes gravitational waves propagate at the speed of light. The scalar sector is less straightforward, but still these graphs show that this is entirely healthy. So no gradient or ghost instabilities, and also safely subliminal propagation. But this choice for the tensor sector was deliberate, so to speak. It makes the whole calculation quite easy, but this is tricky in a way, because we need to ensure that our solution remains luminal at most, we need to ensure that we do not have superluminal propagation, not only on the solution itself, but also in its vicinity. So we need to check what is the behavior of the theory in the vicinity of our solution, which wasn't initially done. So we had to get back to this question and explore it separately. So let us see what happens around the solution. Here is the graph which shows the variance of the tensor speed. The x-axis stands for pi, and the y-axis stands for pi dot. So our solution, which is pi equal to t, is this horizontal line. And we can see that our solution lies right on the verge of the superluminal domain, which means that actually there is a threat of superluminality for our solution. But this is easy to fix, because it was our choice to take the tensor speed equal to 1 at all times, but we can easily change it by taking another set of Lagrangian functions and make the tensor speed safely less than 1 around the bouncing epoch. So this basically moves our solution safely away from the superluminal zone. And here I should stress that we know our theory only in a small vicinity of the solution. So basically, this superluminal domain, which is pretty far away from the solution, is no threat for us, because we cannot say anything definite about our theory at that distance. So far, so good. We can ensure that our solution is safely subliminal by making a thoughtful choice of the Lagrangian functions. Another interesting question in this regard: what happens if we add another method to our setup? This is interesting because it was shown in the work of Eason, Savitsky, and Wickman that, for instance, the Gensis scenario suffers from superluminality if one adds just a small amount of a perfect fluid into the setup. So it is worth checking if we have the same problem here or not. So let us add an ideal fluid. Naturally, the background is modified. However, tensor sector remains unchanged because neither of the coefficients involve the Hubble parameter. The scalar sector acquires an additional mode, which was velocity potential in our case. The stability conditions get modified naturally, but what is interesting is that now these two scalar degrees of freedom in the system get considerably mixed. So here you may see the sound speeds for both modes. From the first glance, we can see that one of them is greater than the other. And US here is the sound speed in the absence of gravity. And while the coefficients A and B are also some combinations of the Lagrangian functions and pi and rho, which refer to the ideal fluid. For now, let us see with the specific examples how these two sound speeds behave. Let us take the simple example of radiation. So we take our setup, our solution, which we have found, and add there some small amount of radiation. Let's see what happens with the speeds. One of them has a bump, and this is the speed we have to take care of in the context of superluminality. We have to ensure that we add not that the amount is not big enough to hit the superluminal domain here. While you may see that another speed becomes negative, this is just the gradient instability, and we do not really take care of it here, because actually the model was constructed so so that no other matter was expected. I mean that we can again fix the Lagrangian function so that both speeds will be safely greater than 0 and there would be no instabilities. But for now, let us leave it as it is and pay attention to the speed that might become superluminal. And in the second graph, we show that even if we take a sufficient amount of this radiation, the maximum of this speed, the maximum of this bump, will not exceed the speed of light. So it seems that we are safe here from the superluminality point of view. Okay, let us look at another options. Let us take other matter components with greater speed, with greater sound speeds. The left chart here is for the speed of 3/4, and we see that one of the that here the bigger speed becomes superluminal. But what is good here that this superluminal domain remains within the domain of instability in our model. So in this regard, it is not harmful. But if we take a greater speed, then the superluminality becomes genuine, because this superluminal domain expands into a healthy region, and now this is the problem. Let us take a closer look to the case of the unitary speed for the extra matter, and here I will present an analytical argument. So let us get back to the expressions for the speed. And let us assume that without matter, our setup was stable, meaning that this coefficient A reduces to the standard speed of the scalar modes, and this has to be positive. As soon as we switch on the extra matter, this doesn't ruin the stability if we add a small amount. So the second speed remains positive by continuity. But since this coefficient beta is is positive, because GS is fixed by the stability conditions to be positive, we immediately see that this sound speed with plus becomes superluminal. The interesting thing is that here in this argument, we didn't rely on any specific model. So these expressions are valid for any beyond Harndeski theory with extra matter in the form of the perfect fluid. So we may deduce that any beyond Harndeski setup becomes superluminal if we add even just a small amount of matter whose sound speed equals to that of light. And this is interesting. The same thing was checked when we add to the beyond Harndeski theory a K essence, a scalar field in a quite general form. I will not give the I will not stop on this example here, but instead I will generalize right away to the DHOST 1A subclass, where we have carried out the same calculations. Namely, let us take DHOST 1A and add their k-essence with the standard Lagrangian, where chi is the k-essence and y is the standard kinetic term. We still have 2 degrees of freedom, the curvature perturbation and the perturbation of the k-essence. Now the stability of the scalar sector is governed by these 2 matrices, G and F, which have quite a complicated view since, again, I do not give the explicit forms of some of the coefficients involved here, like GS, FS, and this G small and F small. But I hope that will be enough for to carry out the whole argument. So the scalar speeds obey the following equation and have the following form. We have to get to the cases here. So for small y, so for small y, we have several cases. The first one is when the sound speed of the k-essence doesn't equal to the scalar speed of the pure DHOST 1A. Then one of the speed is unmodified and has the same form as it used before. And the second one is requires this addition, this additive, which in the case when F doesn't equal to G, when these coefficients are not the same, we see that this speed, if the speed of the k-essence equals to the speed of light, the speed of the delta chi becomes greater than 0. So we end up with the superluminality here right away. The same in the second case, when we have equal speeds, then both speeds have this form, and the one with the plus, again, in the case when F doesn't equal to G, is greater than the speed of light. So this means that in a general case, one of the scalar modes is superluminal if the speed of the k-essence equals to that of light. But we both cases indicate that the case of F equal to G is somewhat special. So let us see if it is so. And indeed, if F equals to G, then the matrix which gives us the sound speeds is triangular for any value of y. And this gives that this indicates that one of the speeds is unmodified, and the second one, I do not give the explicit expression here, but it is not necessarily superluminal. The expression is quite bulky and not really illuminating, but anyway, we cannot say anything definite about it, unlike the previous cases. And this equality, F equals to G, gives us a special constraint on the DHOST 1A Lagrangian. Namely, it relates one of the free functions with the other 2. And this gives us a special subclass of DHOST 1A theories which do not possess an inevitable superluminality, unlike the others. Interestingly, this subclass contains Hardesky theories as a special case, and it doesn't involve beyond Hardesky theory, for which the superluminality is inevitable. So let me get to the conclusions. We have shown that there exists a completely stable balancing solution beyond Hardesky theory with the extra matter. the extra matter might be radiation or have this parameter omega somewhat larger. This might be interesting from the point of view of incorporating the bouncing scenario in a more general cosmological models. We have also shown that in a cosmological setting, any Bianchi-Andreeschi model suffers from superluminality if we add any amount of, even a small amount of luminal matter. This holds for both, this was shown for both ideal fluid and the K essence. And the latest result that was obtained is that DHOST 1A theories differ from the Bianchi-Andreeschi case, so to speak. Namely, DHOST 1A contain a special subclass where the addition of a luminal scalar doesn't necessarily induce a superluminal mode. So thank you for your attention. If you have any questions, please feel free to ask. I believe I'm quite ahead of the time.
Yeah, thank you very much, Victoria. Yes, you finished like 5 minutes earlier, but that's fine. We have some time for questions. Please, if anyone has questions, please go ahead and ask.
Okay.
So let me ask a question. So you say you included K essence at some moment to see if it's if it leads to superluminality, but and at the same time you are talking about the including the luminal matter in the Lagrangian. So I'm a bit confused. So because K essence is never luminal unless it is a standard kinetic, has a standard kinetic term, right?
Yeah, that's right. It might be my bad wording here because, oh, I'm sorry for the notes. Actually, our deductions hold for the case of the conventional scalar field with the conventional kinetic term, whose speed equals to 1. So in a general case, K essence is not the case, but if the scalar field, the additional scalar field has the luminal speed, then one of the scalar modes inevitably becomes superluminal. That was the statement, actually.
Mm-hmm. I see. And so, also about the DHOST 1A theories.
Yeah.
So you actually did not, is it correct that you did not prove that any luminal or subluminal theory doesn't lead to superluminal mode? You, as I understand, you provided some examples. Yeah, is it correct?
Well, what we expected is that the result of Bianchi-Andreeschi would be the same in a larger subclass in DHOST 1A, but that was not the case. We cannot say for sure that if we add the luminal matter to DHOST 1A, we inevitably get superluminality. No, we have shown that there is a special subclass where it is not the case.
Mm-hmm.
So there is uncertainty about DHOST 1A. You'll need to study this separately in every not every, but in every special case.
So yeah, I see. So what can you say if let's say you take this DHOST 1A, which looks good for you, yeah, and then I try to do some non-cosmological physics, like doing black holes or something. Do you still expect that everything will be totally fine there?
Hard to say actually, because we didn't look at this matter even in a narrow subclasses like Hardesky and beyond Hardesky. Anyway, I actually don't know how to answer. Sorry.
Okay. Okay. So
that doesn't have the gut here for this.
Thanks a lot. Are there other questions?
I have a question.
Please.
Is there wormhole solutions in this theory? It's not directly what you are talking about. I'm asking because I was working on theory with non-minimal coupling, and we found some wormholes. And my next project, I thought, would be to study this kind of theories and wormholes, but maybe there are already, and that's my question, if you know in this direction.
Well, in fact, our group is working on this matter. Namely, we were looking for the wormholes in beyond Hardesky, especially, and we were thinking about, we were working on the expansion to DHOST 1A, for instance, or DHOST theories in general. And this is the future project. I believe Sergei Mironov, who is here, his talk will cover your question for sure. He will talk about wormholes in beyond Hardesky theory, and probably he'll say a couple of words about DHOST also.
Okay, thank you.
So his talk will be tomorrow in the morning session. If anyone wants to see wormholes. Please, any other questions?
Zhenya, you mean the talk was yesterday, right?
Yeah, maybe.
With the wormholes, that's easy to imagine, right?
Right. So, Alex, do you have a question, or you want to talk about your mimetic mix?
I can start with mimetic mix, and maybe I will ask Vika some questions later.
Okay.
No, please go ahead, because
look,
we
I
have
could
time.
not properly concentrate because I was thinking about my mixtures.
Okay, please then
watch it on YouTube and then ask properly.
Okay.
Yeah, if there are some other questions.
Yeah,
there is a question from Kevich.
Please, I cannot hear you. There was a question.
Zhenya, there was Maxim Fitkevich, no?
Yeah, he's raising hand.
Please, please go ahead. Maxim?
Maxim, you need to switch your microphone.
Your microphone is off.
I have a rather naive question. Why superluminality is so bad in this series? Why we cannot consider superluminal modes and maybe some mechanism like chronology protection to spoil them off? So my question is about this.
Well, the answer is quite simple. We're lazy enough to deal with some non-standard UV completion, so we just opt for a simpler version. Like if we avoid superluminality, then everything is fine, and we can expect that Lorentz covariant UV completion is still possible. But there are other options, and some people debate that there are no threats in superluminality, but still, we have chosen the simplest option. That's it.
Okay, thank you.
Other questions? I don't see any hands raised. All right, Vika, thanks again.